Hello everyone. Today I am going to explain about one method, that is super resolution method. This method is mainly used to detect or estimate the highly resoluted images. So actually this method is mainly used in some medical fields. Why? Because in medical fields correct desired output image is required. That's why we are using this method, and mainly in medical fields to estimate or to detect the correct spot of the diagnosis, highly resoluted images are required. So that this method is mainly used in medical images. In firstly abstract mode, as I mentioned earlier, we are going to estimate the highly resoluted image by using this method from the database. So we are going to give some of the patches also in database. Those are going to be in database. The patches means firstly group of pixels we are going to known as patches, and secondly the name is known as non-negative sparse linear representation. We can name it as a non-negative sparse linear combinations. We are going to get a clear idea about this method in further slides. After that, the coefficients of the representation. This method strongly depend upon the similarity between the input patch and the sample patches in the database. That means a database contains number of patches are there in the database. So if we are giving a single low resolution patch, that must be similar to the database patches, so that we are giving similar patches into the database. Then only we are expecting highly resoluted patches. This is the clear idea about this method. Let's look into these pictures. This is the low resoluted noise images, and it contains some additive white gas and noise, and we are estimating the highly resoluted image. This is the knee part of our human being. We are going to estimate the highly resoluted images. So by using this method, we are going to estimate the HR image. Okay, firstly, as I mentioned earlier, this method is mainly used in some medical field. Firstly, let's assume if we are giving a low resolution input image as Y, I am assuming like that. I am assuming HR image as X, and the image contains n number of patches are there, so that the size is root m by root m. I am making this input image as some n number of patches, and definitely we are going to get n number of patches. So in expected highly resoluted patch image also, so that we are making X is equal to, I'm visualizing like this. It also contains highly resoluted image, also contains n number of patches with size root n by root n, and the relation between the sizes of HR image and LR image. LR means low resoluted image and HR means highly resoluted images. This is the relation root n is equal to S into root m. We know that these are the representations of the images of LR image and HR images. Now I am going to give the one relation between these images. That is, this is the equation. So by this equation, we are going to get low resolution image from XIH. XIH is the highly resoluted image. So this is the relation between low resoluted patch and highly resoluted patch with some additional noise, and noise contains mean 0 and variance sigma I square. And D is the decimation operator, H is the blur operator. So by using this equation, we are going to get the low resoluted patches. This is the relation. As I mentioned earlier, the image contains n number of patches, so that the expected highly resoluted image is I'm making in terms of vector, that is R power n, and low resoluted image also I'm representing in terms of vector R power m. It contains m number of patches, and here itself algorithm contains totally two phases. In first phase, database construction phase, and second phase is super resolution reconstruction phase. Okay, let's take first phase, database construction phase. That means that there are many sample images are there. Among the all sample images, we are going to extract the similar patches as similar to the given LR images. The database may contain high resolution patches or low resolution patches, but those all patches are very similar to the given low resolution patch or expected HR patches. So I'm extracting the highly resolution patches from the data from the standard images and denoted as PKH, and the size is root n by root n. And we know that we are going to get the low resolution patches from this equation. So that we know this is the highly resolution patches, HR patches, and I'm going to determine the LR patches also. Okay, this is the relation between the LR patches and HR patches. Initially, we are extracting the HR patches from the database, and we are making low resolution patches also. So that at this point of time, we'll have both LR patches and HR patches. I am representing those in terms of pair. This is the total entire low resolution patches database, and this is the entire highly resolution patches database. And I am making this database into some normalizing forms. These are the normalizing forms. UKL is the normalizing form of the low resolution LR patches. That is PKL by name of this one, and UKH is the normalized form of the HR patches. That is PKH by name of this one. So this norm form is very similar to this PKL also. So that's why I'm replacing this PKH into UKH and PKL into UKL. Why I'm replacing means I'm going to find out the relation between name of the LR patch to HR patch. That's why I'm replacing. After replacing, we will get the relation UKL is equal to this relation, and from this relation I'm going to convert into, now I'm interested in to find the relation between total entire LR patch database, entire HR patch database. So that's why I'm replacing this UKL and UKH into some PH and PL, entire databases. So by using this relation, we are going to get this one, PL is equal to DSH PH. This is the relation between entire LR patch and entire HR patch. So at this point of time, we are clear about the database. Now we have entire HR patches and entire LR patches. So clearly we are extracting the database from the sample images. And further step is super resolution construction phase. In this phase, firstly we are going to reconstruct the only one patch. So after reconstructing the all patches and after combining the all patches, we are going to get the entire highly resoluted image. So firstly, we are reconstructing the single patch. As I mentioned earlier, we have to take very similar images in database as that of the input image or that of the highly resoluted images. So expected highly resoluted image XIH is I'm making it as linear combinations of the all highly resoluted patches in the database. This is the formula for linear combination, and with one vector alpha k. This is a scaling factor. It contains number of elements are there, and we are named it as a sparse vector. This sparse vector contains many number of elements are there. And after that, I am replacing the summation, whole summation into PH. Why? Because this is the entire database of the highly resoluted patches. So that I am replacing this highly resoluted patches into database, and some with there is additionally some alpha is there. It is a sparse vector, and this is the main equation for this method. We are going to get the highly resoluted patches by using some database and with some additional sparse vector. So nextly, we have to find, we don't know the alpha I values. We want to find out the alpha I values. So that I'm going to give some just basic idea about how to find out the alpha I values. So for that, I'm multiplying both side DSH into DSH. So like that, I'm multiplying both side, and we know that this entire part DSHPH, this entire patch is named as the low resolution database PL, and I'm replacing PL, and this thing DSHXIH, and this thing is replaced by PL alpha I in equation 1. In this equation 1, this entire thing is replaced by PL, and that means entire database low resolution patches into some alpha vector. I'm replacing like that. Just look at this equation. I'm replacing the entire equation, this entire term into PL into alpha I plus some additional noise is there. After taking the term into left side, and after that I'm taking power of this equation. The power of the additional noise is sigma I square, and I'm making it. I'm representing it as zeta I, and to calculate the power of this term, I'm taking norm of this term. So from this equation, we are going to get the alpha I values. If we know about the only sigma I values only, if we know sigma I square values, by replacing those values, now we are going to get the alpha I values. So from this basic idea, we are going to get alpha I values. There is one assumption is there initially. The input image contains only positive intensity values. We are assuming like that, so that estimated output image also contains positive intensities only. So that's why I'm going to take those alpha values into positive values only. So I'm making those alpha values are only positive. I'm assuming like that. After that, what sort of properties are there for getting these alpha values, and correct idea behind that, those things are explained by my friend. Thank you.
The high resolution estimated patch can find out by the sparse vector alpha I combination times high resolution database set. Since we are taking the patches UKH very similar to XIH, we need to find in the patches which are dissimilar to XIH. So we came across this function alpha equal to alpha equation, which actually the main theme of this is in order to the approximate the low resolution patch to the combinations of database low resolution patches. So in order to find the similarity patches, we here introduce omega ik as a penalty coefficient. It means if there is high dissimilarity, omega ik is very large. So we nullify it by taking alpha ik value, which is very similar, which is very small as shown here. So the penalty coefficient can be written as the pi of dissimilarity between low resolution input patch and low resolution input database patch. So in order to find the dissimilarity between these two, we can use Euclidean distance property or congruence property. Here we are using congruence property because Euclidean distance property due to the addition of noise may not be effective. But congruence property says that if two x1 equal to u x2, we can easily say that these are congruent. So in order to find the expected value, we apply expected value or hold the equation. So we can find out through this method. So the dissimilarity between these two patches can be written as the norm of low resolution patch in and database low resolution patch plus where IK is referred to the noise constant, and we are introducing a phi function uh, which amplifies if the value is greater than a particular threshold value, and it remains same for less than particular threshold value. So if there is ideally dissimilarity, it means it will be equal to only norm of noise. So using some Lagrange multiplier equation, we add some more terms. I is for the sparsity and fidelity of the patch value, and YL is to approximate to the database patches. So these coefficients, summation of these coefficients can be written as two vector products. So the whole equation can be find such that we will get to the very accurate value of alpha. It is known as non-negative quadratic programming. We can find the high resolution patches alpha k and UKH, where UKH are the high resolution database patches and alpha AK is the sparse vector. So similarly, we can find out the low resolution means denoising patch through the sparse vector combination over the very similar patches, low resolution patches. In order to construct the entire image, we set all patches on the HR grid, means high resolution grid. So wherever there is a overlapping portion, we will average it to the portion. So similarly, we set all the low resolution patches and overlap and average the overlapping regions in order to get denatched image. So in order to get very fine high resolution image, we are making to back projection algorithm. It means we are iterating the high resolution image such that uh, the decimation factor and deblurring factor times the high resolution patch equal to the denoise patch of Y. So in this closure, we are taking the advantage of database patches and getting the high resolution image from the low resolution input image. Here are the some results. Resolution image with noise, high resolution image, standard super resolution and denoising method. So similarly here also low resolution image to resolution super resolution and denoising method. These are the references we take.